Welcome to Chapter 17 of MEC410, Design of Machine Elements. This week we're going to study linear motion elements. You've got 5 relatively simple homework assignments, and for the last 3 I've given you some constants that are not noted in the textbook for you to use. Here's some examples of linear motion elements. The simplest one is a linear solenoid. You give the solenoid a voltage and this little pin moves in and out. Here is a lead screw that we'll cover in this chapter, in which you rotate the screw and this nut translates up and down on the lead screw depending on which direction the screw rotates. A fluid power cylinder is similar to a solenoid in that this cylinder moves in a line in and out, and that depends on the fluid pressure that is put into the cylinder. This mechanism up top here is the most complex. It is a power screw. You have a motor that rotates the worm. The worm in turn rotates the worm gear. As the worm gear rotates, this thread goes through the nut and this thread moves up and down. On top you have the load pad, and that's where you would put a very heavy item to lift up and down. Lead screws are used in machine tools, XY tables, actuators on aircraft. Here on the left side is a simple example of a lead screw that is the manually driven axis of a milling machine. If you rotate this handle, the lead screw turns, and then the whole table moves across in one axis as you're doing your milling work. This is a section view of a ball screw. You have a DC motor that rotates the screw, and then there's a nut in it that moves up and down. Here's your ball screw nut. You also have support threads that are needed. You have a clutch in it. You have bearings. You have a lot of the components that we had in our Chapter 15 Design Project 1. There's 2 types of threads used in power screws. A square thread is the simplest one. The cross section of the threads is literally a square. What is more common is the Acme thread, which here you've got a thread that's on more of a slope and an angle. If you do a section cut on this axis through the thread, you'll see that you have a trapezoidal opening in the thread, typically at 29-degree included angle. The pitch on these threads is defined as that for screw threads or for a worm. You take one point on the thread and you find what is the axial distance to the exact same point one thread over. Our book in table 17-1 gives you all the dimensions you need to know for Acme screw threads. First column gives you the major diameter in inches, and threads per inch is in the second column. The pitch in the third column is 1 over the threads per inch. In the fourth and fifth columns we have the minimum minor diameter and minimum pitch diameters. And the most important information you get is the tensile stress area, which you use to calculate tensile stress in the thread if you know what the axial force is. And you also are given the shear stress area for the different screw thread sizes, which you would use if you want to calculate the shear stress for a given shear force. This slide shows you the torque you need to move a load up, meaning against gravity, with a square thread. You need to know how much torque must be applied to the nut of the screw to move the load, because the torque is coming from a motor or a motor in a gear system, and you need to know what torque output that system has to supply. The parameters involved are the force F that you need to move, which if you're moving up is often just the weight of something. The size of the screw thread is indicated by its pitch diameter, d sub p, the lead of the screw L, and the coefficient of friction F. And here's the equation on the bottom, which involves all those parameters. If you want to lower a load, the torque is not 0. And the reason the torque is not 0 is because the frictional force in the threads opposes the load as it comes back down. Now certainly the torque down is less than the torque up, but I'm just pointing out that because you don't have frictionless screw threads, there still is a certain amount of torque that you need. In order to calculate the efficiency of a power screw with a square thread, we first find the torque T prime required to move the power screw up, assuming small f, the coefficient of friction, equals 0. So we take this equation, 17-2, for T up, and we set small f equal to 0. And we find that the torque with 0 friction is just F times L divided by 2 pi. Then the efficiency is the torque with 0 friction divided by the actual torque up, and that's equal to FL divided by 2 pi times T up. Here is what F and L would stand for in the power screw of a machine tool. F is the weight of the table and machine parts sitting on the power screw, and L is the travel distance of the table in one turn of the manual crank. The equations for a power screw with an Acme thread get more complicated, and that's because the force F that in the square thread was a parallel to the direction of motion and to the lead is no longer parallel. Its force F to move up or move down is angled on this surface, the side of the Acme thread, and that force on the side of the Acme thread is now F divided by cosine phi. In addition, we have to use the lead angle, lambda, which is defined similarly as we did for the worm. The tangent of lambda equals L, the lead, divided by pi times the pitch diameter. And when we reevaluate the torque to raise the load with an Acme thread, we have this more complex equation here in the upper right, 17-10. And the torque to lower the load is also more complex. It's equation 17-11 shown here. And the power is just the torque times the rotational speed in RPM of the power screw divided by 63,000. A ball screw is a more complex mechanism than a power screw. The ball screw, as shown here on the bottom, consists of a screw and nut, each with matching helical grooves. So there's your helical groove here. And the balls roll between these grooves, providing the only contact between the nut, that's this blue part, and the screw. And because of that, the friction is very low. The balls exit from their pathway, going around and around as the screw rotates, into a recirculating raceway, that's here, and then they come back to the beginning of the line and go around and around and recirculate again. And the ball nut determines the load and life of the ball screw assembly, and the ratio of the number of threads in the ball nut circuit. Here the ball nut circuit shown has 5 threads, to the total number of threads in the ball screw determines how much sooner the ball nut will reach fatigue failure than the ball screw. The rating of ball screws gives the load capacity of the screw for a given life, which is 90% of the screws of a given design will survive. And this is similar to the L10 definition we had for ball bearings. But because the ball screws are used as linear actuators, the most relevant parameter is the distance traveled by the nut relative to the screw. And manufacturers usually report the rated load that a given screw can exert for 1,000,000 inches, which is 25.4 kilometers of cumulative travel. And the relationship between load P and life L is also similar to a ball bearing. It's given by the equation L2 over L1 equals P1 over P2 cubed, where L1 is typically the 1,000,000 inches of travel, and P1 is the load that was turned during those 1,000,000 inches of travel. L2 is a different number of inches of travel, and P2 is a different load used. But in our textbook, we make it easy for you. Figure 17-8 summarizes ball screw performance. And all you really need to know to select the ball screw is how many pounds you want to move with the screw here on the y-axis. And on the x-axis, you have to calculate the total travel life in inches of the screw. And once you calculate that total life and you read across with the load, you get a point somewhere on this graph, and you select the line that's directly above your point, which then tells you what is the nominal diameter of the ball screw to select, what's the threads per inch, and what's the lead of the ball screw. The efficiency of the ball screw is typically taken to be 90%, but that doesn't mean that every ball screw really runs at 90% efficiency. But far less torque is required to exert a given load on a ball screw than for a power screw. Power screws typically have 20 to 30% efficiency, and so the power for a ball screw to move a load is much, much less. On the other hand, ball screws cost a lot more money than power screws. The efficiency of a ball screw is E equals FL over 2 pi times T up. And if we use E equals 0.9, that equation devolves to T up equals 0.177 FL. But if the efficiency is some number other than 0.9, then you need to use the long form of the equation. Because of the low friction, ball screws don't self-lock the way worms do. But you can apply a load direct to the nut in order to rotate the screw. Normally in ball screws you rotate the screw and the nut moves, but another way that you can run a ball screw mechanism is to push on the nut and then the screw starts to rotate. And when you do that, it's called backdriving. And the backdriving torque for a ball screw is FLE over 2 pi. E is now in the numerator, not the denominator. And you get the backdriving torque is 0.143 times FL, but only when E equals 90%. Here's example of problem 17-3 for you. The goal is to select a suitable ball screw for an application which was described in examples 17-1 and 17-2, illustrated in figure 17-4. And the idea was for a hatch to be lifted 15 inches to open 8 times a day and then closed. Do this for 10 years, and lifting and lowering must be completed in no more than 12 seconds. Here's a figure 17-4. You've got a hatch and a 25,000 pound load on it, and the hatch is connected with a frame. The frame is connected to the nuts, one here, one there, and each of the nuts is connected to a set of Acme screws. And the Acme screws are raising the hatch. But in this application, they want us to use a ball screw to raise the hatch rather than the Acme screw. The Acme screw was actually for example 17-1 and 17-2, but now we're up to example 17-3. We approach this problem by setting up an equation that can calculate the travel of the ball screw based on all the other parameters given. And all the other parameters given are shown here in this gray-filled area. We've got efficiency, motion of the ball screw, number of strokes to open or close, and a simple and straightforward formula to use for the travel life of the ball screw is to multiply all these numbers together. And it's 8.76 times 10 to the 5th inches. Our goal using a figure 17-8 is to pick which ball screw to use. On the x-axis, we have 8.76 times 10 to the 5th to draw a line up. On the y-axis, we have a load of 12,500 pounds, draw a line across. Where they meet is this point right here where my mouse is. Therefore, you select this blue line directly above it, which says that our ball screw should have a 2-inch nominal diameter, 2 threads per inch, and a lead of 0.5. If you want to calculate how many inches this ball screw can survive at a load of 12,500 pounds. You take a horizontal line from where your original point was at 8.76 times 10 to the 5th, and you draw a cross until you hit the blue line for our power screw, and then you come down approximately where you will land on this x-axis is 3.2 times 10 to the 6th, so roughly 3.2 million inches of travel life. What we do next is to calculate the torque required to turn the screw, and that torque at a 90% efficiency is just 0.177 times the force of 12,500 pounds times the lead L of ½ an inch. That's 1,106 inch-pounds. We calculate the rotational speed N at 150 RPM from this equation where my mouse is. And the power then required for each one of these screws is 2.634 horsepower. The rated travel life for 12,500 pounds load is 3.2 times 10 to the 6th inches. And the ratio of rated to actual travel life is 3.2 times 10 to the 6th divided by 8.76 times 10 to the 5th, which is a ratio of 3.65. These next two slides will show you some commercial examples of linear motion elements, and also how expensive they are. This top one is called a ball screw linear actuator. They're going between $800 and $1,200. This next one is a precision ball screw with nuts, somewhere between $300 and $1,000, both from Grainger. You can buy a programmable actuator, which includes a motor on it, and that's between $200 and $1,000. Or you can buy the deluxe FT series electric linear actuator, which has extremely high force, fairly high speed, has multiple models, sizes with planetary roller screws, and it's going to cost you between $1,000 and $2,000. Or you can buy another model called GSX Series Integrated Motor Actuator from Grainger with less force, only 11,000 and change, and slower speeds, but that'll still cost you between $1,000 and $2,000. So the moral of the story is, don't specify linear motion elements unless your design can afford it.